Hi everyone. Today we're going to be looking at 6.4, which is on geometric sequences. Now we just finished up 3.4, arithmetic sequences. Geometric sequences is just another type of sequence that we're going to be looking at in this unit. I want to start with this warm-up. A seating plan is being designed for section 12 of a new stadium. If I look at each of these rows, row A, B, C, D, and E, I notice that in row A we have 2 seats, in row B we have 5 seats, in row C we have 8 seats. If we were to describe this pattern, 2 and then 5 and then 8, I would expect in row D to have 11 seats. And if we go up here and check 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, yes, there are indeed 11 seats. This follows the pattern that I see here, and that each row you add 3 seats. Okay, so here's our pattern here. If I wanted to write an equation for this pattern, because we have an additive rate of change or a common difference, I know that this can be modeled using an arithmetic sequence. Now let's go ahead and, as a reminder, let's go ahead and write the explicit formula for this arithmetic sequence. A sub n is equal to the first term, 2, plus the quantity n minus 1 times the common difference, which in this case is 3. We're adding 3 each time. Okay? Now, if we were to simplify this, this would be a sub n is equal to 2 plus distributing that 3, we get 3n minus 3. And then simplifying further, we get 3n minus 1. Okay? So row Z of section 12 must have at least 75 seats. If the pattern continues, does this seating plan meet that requirement? Justify your answer. So I need to know if row Z, which by the way is the 26th letter of the alphabet, it's the last letter, therefore N in this case is the number row, or 26 in this case. So I want to know, is this greater than 75 seats? So let's go ahead and plug this in. This would be A of 26 is equal to 3 times 26 minus 1. Well, this is equal to 3 times 26 is 78, minus 1 is 77. So because 77 is greater than 75, yes, the requirement is met. Great. So here we just did a warm-up, and this was an arithmetic sequence. The other type of sequence that we're going to be looking at in this unit is geometric sequences. A geometric sequence is a number sequence in which each term after the first term is found by multiplying the previous term by a common ratio. So just like in a arithmetic sequence where we have a common difference, we're adding or subtracting a number from the previous term, we can multiply the previous term by a common ratio, and that's going to give us that geometric sequence. Arithmetic sequences have an additive rate of change called the common difference, whereas the geometric sequences have a multiplicative rate of change called the common ratio. Okay, so I want to determine whether these sequences here are arithmetic, geometric, or neither, and I need to justify my answer. So if I'm looking at sequence A, we're going from 3 to 2. That would be like subtracting 1, or from 2 to 4/3, that'd be like subtracting 2/3, right? Because we're not subtracting the same amount, we know that this is not arithmetic. Well, let's see if we can take the ratio of subsequent terms and see if it has a common ratio. So if I were to take 2 divided by 3, well, then that ratio from the first to the second term is 2/3. If I were to take 4/3 and then divide it by the previous term 2, this would be equal to 2/3. So that holds as well. If I were to take 8/9 and then divide it by 4/3, then this would be equal to 8 divided by 4 and 9 divided by 3. This would be 2/3. So yeah, we get this common ratio um, as we move to the right in the sequence. So this is a geometric sequence. And then because it has a common ratio of 2/3. All right. For part B, here we have 3 to 4.5, 4.5 to 6, 6 to 7.5, and 7.5 to 9. each time we are adding 1.5. So because we have an additive rate of change, this would be an arithmetic sequence, which has a common difference. Okay, go ahead and flip the page. So just like arithmetic sequences, geometric sequences can also have a recursive formula. Recall that a recursive formula has an initial value and a rule. So example 2, given the sequence 1, 4, 16, 64, 256, I notice that we follow the pattern. We're multiplying by 4. So every time we multiply by 4. So the next term in this sequence would be multiply by 4. We would get 256 times 4, or 1024. And then part B, to get to the next term in the sequence, we multiply by 4. Okay? So again, recursive, we need that initial value, which is 1, and then that rule, which is that common difference. Okay, we're saying take the previous term and multiply it by 4. We also have explicit formulas. So geometric sequences, like arithmetic sequences, have explicit formulas where it represents the nth term in the sequence. So here we have a sub n, which is the nth term in the sequence, is equal to the initial value, that first term, a sub 1, times r, the common ratio, raised to the power n minus 1. So example 3, what is the eighth term in the sequence shown in example 2? So if I were looking here at example 2, 1, 4, 16, 64, 256, and so on, we know that the initial value is 1. So let's go ahead and write this out. an equals, actually we're trying to find a8. So a sub 8 is equal to a1, which we know is 1, times the common ratio, which we said we're multiplying by 4 each time, and then raised to the power n minus 1, which is 8 minus 1. So then this must be equal to 1 times 4 to the 7th, which is equal to, if you plug that into your calculator, 16,384. Remember, 4 to the 7th is equal to 4 times 4 times 4 times 4 times 4 times 4 times 4. 7 times. Example 4, the number of subscribers to a blog doubles each week. In the first week, the number of subscribers was 5. Okay, so because this number of subscribers doubles, we know that the common ratio is being multiplied by 2. It's doubling each week. And in the first week, the number of subscribers was 5. This is our initial value. Therefore, we can write an explicit formula. A sub n is equal to a sub 1, which is 5, times the common ratio, 2, to the n minus 1. So if I wanted to write an exponential formula that's going to model the number of subscribers each week, this would be modeled as f of x is equal to 5 times 2 to the x, where the initial value is 5 and the growth factor, or the constant ratio, is 2. So how are these representations similar and how are they different? Well, they both have a constant ratio of 2. I'm going to say a common ratio or a constant ratio of 2 and an initial value of 5. Okay, so we can see that the exponential model and the geometric sequence have a lot of similarities here. They both have that multiplicative rate of change, and they both can be using that initial value, that y-intercept. Okay, so example 5, here we have the number of people attending the annual Town International Food Festival has increased by 7% since the first year. Let's write an explicit formula to find the number of people in attendance in n years. Okay, now because the model is increasing by 7% in the first year, we know that an increase from 6.3 is going to be 100% plus the 7% increase. So this would be 0.07 plus 1. Okay, so that tells us that that's equal to that increase, that rate increase So this is going to be our common ratio R. So the explicit formula is going to be A sub n is equal to, well, A1, which we know is 1250 based on this graphic here. So the initial value is going to be how many attended last year, and then times our common ratio, which is 1.07, and then to the n minus 1. So if this trend continues, what will be the attendance in 10 years? So if we find A sub 10, this would be equal to 1250 times 1.07 to the 10 minus 1. And if we plug this into our calculator, we get 2,298 people. That's quite a bit of people. All right. So I just want to go ahead and summarize here. Here we have the explicit formula, A sub n is equal to that initial value, the first term, A sub 1, times r, the common ratio, raised to the power n minus 1. If you were to plug in some values, we recall subscript notation. This would read A sub 1 is equal to 2. That's saying that the first term in the sequence is 2. Graphically, we see that this has its similarities to exponential functions. We see that the y values are tripling in this instance. They're tripling as you move every term in the sequence. Okay, so this has been our notes on geometric sequences. We're going to get a lot of practice on this, so we'll see you tomorrow. Have a great day, everybody. Goodbye.